Hi, everyone. My name is Nathaniel Frissell. I'm W2NAF, and I'm going to talk to you today about why science in amateur radio is important to drive the future. And I'm very thankful to Hans for inviting me to give the keynote today at this AMSAT South Africa Technical Symposium. It's very exciting to be able to address all of you. I do apologize that I can't be there in person, but 4:30 a.m. Eastern Time, when you have a couple small children, it's just very difficult. So I do appreciate you letting me make this recording. So why is science in amateur radio important for driving both now and the future? And the reason I think I have been asked to give this address is I've started and I lead a group called the Ham Radio Science Citizen Investigation. And this group has been active for a little over 10 years now. And we have three main objectives. And we're looking to advance scientific research and understanding through amateur radio activities. We look to encourage the development of new technologies to support this research. And we look to provide educational opportunities for the amateur community and the general public. And I started this group back when I was a graduate student at Virginia Tech, working on studying the ionosphere. And the reason is, I actually became a professor and became what I am today because of amateur radio. I found amateur radio fascinating from a young age, and I just followed it. And it's taken me some really amazing places. And we now have a fantastic community of volunteers and citizen scientists all over the world. And although amateur radio, or ham-sci, although ham-sci has really been an official thing for only 10 years, really what ham-sci and what AMSAT in terms of science are doing is not new to ham radio at all. In fact, if you go back and you look into history, you can find out that amateur radio has over 100-year history with making advances in science. And in fact, amateur radio helped discover the ionosphere. Early amateur radio played major roles in developing the framework for large-scale citizen science and discovering the ionosphere. So a couple of years ago at the ham-sci workshop, we had a keynote speaker named Dr. Chen-Peng Yang, who is now a professor at the University of Toronto, and he wrote a book called Probing the Sky with Radio Waves. And many of the slides I'm going to show you right now and some of the stories are chronicled in this, and you can see his original keynote address to us there. There's a couple of things that I wanted to point out from his talk. One is he really made the point that science has long been used as a justification for amateur radio. Back in 1912 in the United States, we were restricted as amateur radio operators to use wavelengths shorter than 200 meters. And American ham radio societies, such as the American Radio Relay League, they used experimentation to legitimate their lobbying for the amateur right to the spectrum. And so today, in the United States, Part 97 of the FCC rules states that a primary purpose of the amateur radio service is a continuation and extension of the amateur's proven ability to contribute to the advancement of radio art. Now, I know you're in South Africa and not in the United States, but I imagine that you have very similar fights sometimes where people say, why is amateur radio important? Why do we dedicate resources to this? And so there's a long history of showing that amateur radio really contributes to the scientific good of all of humanity. So there are some very early experiments that were done on a large scale, similar to what happens today. One of the first ones happened in 1920 to 1921, and this was a collaboration between the National Bureau of Standards and the American Radio Relay League, and they were known as the fading trials. And this was a well-structured call for the amateur radio communities to submit signal reports to help understand radio signal fading. This generated thousands of records. Now, the data's scientific significance from this particular experiment was unclear, but what this really did was lay the model for what we now have as large-scale citizen science campaigns. Just a couple of years later, or even just a year later, there was a successful large-scale citizen science campaign involving amateur radio that looked to address this particular question. Starting in the early 1900s, there were a number of different theories that had come about to try to explain how radio signals travel around the Earth. There's a surface diffraction theory where the Earth is treated as a perfect conductor and signals, shortwave signals just travel along the surface of the Earth. There's an atmospheric reflection theory where you have two perfect conductors in boundary conditions. And then there's the ionic refraction theory, which is what we know today is the truest of these, where you have an ionized gas causing different layers of refractive index that allow the signals to be bent back to Earth. Back when all of this was being debated, there was lots of mathematical theories that were being put out, but there was very little evidence to support one versus the other. And one of the reasons for that is just because of the large scale of the problem. In order to make measurements of this, you really had to have people spread out all over the globe or over long distances able to make measurements. And it just wasn't something that was very feasible for, say, a single entity, a single government, single military, a single company or educational institution to do. And so it's really the ARRL Radio Society of Great Britain transatlantic tests, which ran from 1921 to 1924, where they asked amateur radio operators to both transmit and listen on the short waves on both sides of the Atlantic Ocean, that they were able to provide the first conclusive evidence that this theory is actually true. And this demonstrated, this provided experimental data for the science question of which theory is it, ionic refraction theory, but it also demonstrated that low power shortwave stations could communicate long distances rather than requiring massive commercial transmitters, as was thought at the time. So this was really groundbreaking. And the reason that these things were possible is amateur radio science is unique. It's not simply that our community has made major contributions to science and engineering, but rather the way we can work is fundamentally different than what can be done in a laboratory setting or a traditional science setting. And again, there's one of the reasons for this is what we're trying to study is just so large. You know, we're located here on Earth. We're actually trying to understand this entire geospace system. The fact that we have so many people that will voluntarily contribute their time and efforts to understand what's going on makes this very unique. So what are some characteristics of large-scale amateur radio science? It allows for large-scale coordinated campaigns. It's different from what's done in a laboratory. You may have less control because you have different amateurs doing things differently, but you can get a more global view. And this global view is critical for advancing large-scale Earth and space science. And I think one of the most important things I've learned from working with the ham sci community and the amateur radio community and reading about these things is the different perspectives that people bring to the table. Each person, amateur or professional, can contribute a different piece to the puzzle. And that means each of you here on the AMSAT South Africa Technical Symposium. So we continue this tradition of science today. As a global amateur radio community, we are in a better place than ever to contribute to science and have science give back to amateur radio. And of course, there are a few big names that we would be absolutely remiss if we didn't acknowledge today, and that includes Joe Taylor and Steve Franke, who've developed WhisperNet and Whisper and FT8 and WSJT and MSK144. And then there's the people that run the networks that collect all of this data, the Whisper Demon Group, the PSK Reporter Group, the Reverse Beacon Network Group, and many, many others in the community. There are so many people that have come together that have built these networks and these technical innovations that have really allowed us to advance science. And I've really personally benefited from this because I've been able to publish on the data that these systems collect. And I was watching, as I was relearning about the old fading tests back in the early 1920s that they said weren't successful because they didn't have enough infrastructure to really make sense of the data. It's really neat because here, 100 years later, I'm able to draw upon the data infrastructure and the technological infrastructure that the amateur radio community has built, and I am actually able to start to answer and publish on some of these questions. And I did this in my 2022 paper, where here you're looking at reverse speaking network, PSK reporter, and WhisperNet data from on 14 megahertz, 20 meters. And we're looking at about 12 hours worth of data here. And you can see there's an oscillation. This is distance between transmitter and receiver on the y-axis here. You can see some oscillations that last about 1.5 to 3 hours right here at the bottom. And this is an example of a traveling ionospheric disturbance moving overhead over the continental United States, and this would show up as fading in radio receivers for people located at this particular area. So I published this back in 2022. I now have a graduate student who's working on a much more advanced climatology of this, and we are now able to start to relate these things back and show them scientific importance to these things. Another fantastic result we've had is the people who've done so much work to develop the tools that will let us make these beautiful HF Doppler spectrograms. So here's one, a recording of the WWV transmitter that's in Colorado. I made this on October 14th, 2023 over at my house, 24 hours of data, and we're looking at plus or minus 5 hertz here. And the reason I picked this particular day is there's an annular eclipse over the United States. And now with the recent advances in GPS disciplined oscillators, such as the ones that Leo Bodner puts out, the work that the Case Western group has done with monitoring HF Doppler shifts, work that Steve Serwin has done and many other people have done with Dopplergrams, you can just see this amazing complexity in the received signal showing ionospheric variation. And here you can see dawn, you can see multi-hop, here you can see the eclipse. And these are all measurements that we are now able to see as amateur radio operators. So the AMSAT program is, I think, just fantastic. I think it's a fantastic effort. I know this is an amateur satellite conference, and I have spoken mostly about amateur radio high frequency communications, and you may be more interested in VHF and UHF communications, or in signals dealing directly with satellites. But I think we all share this same excitement for scientific discovery, and also seeing how the science can drive us towards better engineering. And so I'm looking at the program, which just looks wonderful. And I noticed there's a few talks jumped out at me that really synergize with the sort of work that I'm doing. And one is the Make Meteor Scatter Communication with Your Next Amateur Radio Project, talk by Derek Gravitt, ZS5Y. That is just very well aligned with one of the projects we're doing called the Meteor Scatter QSO Party, where you are using MSK 144 to better understand how meteor scatter reflects off of either the 6 meter reflects off of meteor trails at either 6 meters or 2 meters, and we're trying to advance meteor scatter science there. And I also noticed the SARL Noise Monitoring Project, which is the noise monitoring is really becoming a hot topic in the world today. Of course, as we have rising noise floors, but also we can learn a lot about the physics of how radio signals travel and the ionosphere by monitoring this noise as well. And so that actually synergizes well with what we're doing with the Whisper Demon Grape Personal Space Weather Station project, which my student Owen's going to talk about in a little bit. So what I really wanted to leave you with is this: why do we do science in ham radio? And I think the number one thing is amateur radio science is fun and fascinating. You know, we as amateur radio operators are doing this because we enjoy it. And we really do find some sort of personal satisfaction and interest in this. And that leads us to my second point here. Science gives us purpose. This gives us personal purpose to justify the time we spend doing this. Why do we spend our time working on this, on amateur radio, on science, versus, you know, playing basketball or any of the other activities we might do? It helps give purpose to justify the existence of the amateur radio service when we have to say, why do we have the spectrum that we have? The science helps bring us back to that. I think number three, we have unique capabilities in the amateur radio community that even large research institutions, companies, and governments cannot replicate on their own. We can provide a platform for global measurement and collaboration. We can bring together people with unusual and unique skill sets, expertise, perspectives, and interests. I have projects that have everyone from high school students all the way up through undergraduate students, people working in industry, people who are retired. It's really amazing how the amateur radio community can bring this together. And the science really drives us forward. The unique needs of science forces us to refine our data and our analytical skills and advance our radio engineering in directions we may not otherwise go. You know, one of the things I've learned in working with this scientific field is the old methods of doing amateur radio communication may not provide enough stability or careful measurement or information that we need to answer our science goals. And so then we design systems that can do precision timing and can do precision frequency measurement. And then that in turn can actually help us go back and improve how we do our radio communications. So with that, I hope you have an absolutely fantastic technical symposium today. And I'd like to thank the National Science Foundation and NASA and ARDC and all of the amateur radio community volunteers who have contributed to this work. So thank you.